All right, this is an optimization problem. It's number 52 from section 4.7 in the Stewart text calculus. Whoops. And so we're supposed to find the equation of the line through the point 3,5 that cuts off the least area from the first quadrant. So I've drawn the axes. I've drawn a line through the point 5,3, or sorry, 3,5. And the idea is, this line would have to have a negative slope, right? Anything else is not going to cut off an area from the first quadrant. It would create, two open regions, which would have infinite area. So it's got to have a negative slope. And really the question is just like what slope kind of, is going to, well, we were supposed to find the equation of the line, but, which line is going to make this triangle have the smallest possible area, okay? And there are a few ways to approach this problem. And we actually did this one in class the other day. If you're, in my fall of 2021 class, you might have, we had one student talk about doing it using geometry, where I think we were talking about like looking at these triangles, and that can work. There's 3 triangles here that are all similar because they have some shared angles and some corresponding angles with parallel lines and a common transversal. And so those 3 triangles I just highlighted are definitely similar, which means they have congruent angles, and you can use proportions of side lengths to get this. There's enough there, I'm sure, to do this problem. I want to focus on it more with coordinate geometry. And it's a little tricky. It's easy to get confused or mixed up with the X's and Y's in here and what they represent. And I actually got stuck a little myself yesterday in class when we were doing this one with that issue, but kind of ended up pushing through, in an interesting way. But I want to do it a little differently today. So this line, first of all, we can write the equation of this line. Y equals, you know what, let me start instead. Y, let's say y minus, we have this point slope form, right? We have this point that it passes through. So let's use that point, y minus 5, because you want to use the given information, right? This is like the anchoring point for the line. So I want to make sure I use it in my line, if that makes sense. Y minus 5 equals m times, x minus 3, x minus x1. That's my point slope form. And I could move the 5 over to the other side. And then, we can think about what m is, but I will point out m is variable here, right? Like this line, the idea is it can be rotated at any angle so long as you get a negative slope so that it has an x and a y intercept. All right. So it looks something like this. And the other thing that I need to do probably early on, kind of like to do this right away, is to think about my primary equation. What is the thing that I'm trying to find here? We're trying to find the least area, cut off from the first quadrant. So that area is this triangle, right? So we're trying to make this area as small as possible. That's what we're minimizing. So the first thing I might do is write down that area. Here, I guess I'll just leave that highlighted to kind of match it up. A equals, and it's going to be 1/2 base times height, right? So that's the area of a triangle. So I need this base, and I need this height. And again, you can kind of see how that would fit with the similar triangles geometry approach. But what I'm going to do is I'm going to focus on the equation of the line, like from a coordinate geometry standpoint. And I'm going to say that this y-intercept is, I'll just use b. That's like a pretty typical thing to use for a y-intercept, right? I don't want to use y here. And this is where I was running into a little bit of an issue yesterday. I don't want to use y here because then y represents the y-coordinate of the y-intercept, but then in this, y represents the y-coordinate of any point on the line, and it corresponds with the x-coordinate of any point on the line. And that's problematic. You don't want your y to represent 2 different things, or your x. So if we call that b, and just remember that b is also variable here, that's fine. And then, so this point would be 0, comma b. And then I'm going to do the same thing here. I'll just use a then to go with x because it kind of fits with b for y. And so this point would be a, comma 0. And no matter where you move it, it's an intercept, so those zeros don't change, but a and b do change potentially. And so if I do it this way, now the base of my triangle is A and the height of my triangle is B. And so the area, the area is 1/2 AB. So far, so good. My goal is on any optimization problem to take this, this is a primary equation, right? To take this primary equation, first you need to get it written. And then we want to get it written in terms of one variable instead of two. Right now we have A and B. So we want to maybe use a secondary equation to do that, or maybe multiple secondary equations. First of all, let me point out we are minimizing here. That's not a bad thing to make a note of also. We're minimizing the area because it's the least area. All right. So now I need to relate A to B, and I want to use the equation of my line to do it. And so that's where this gets a little interesting. Now, A and B and 0, the zeros there, those are x and y coordinates of points that are on that line. So I can actually plug those in. I will also point out that M is a slope of the line, and we can actually write M in terms of A and B if it would be helpful. So maybe it will. I'll just make a note of that while I'm thinking of secondary equations here, right? So this is a secondary equation. I'll just write SE for that, meaning I'm going to use it to help me eliminate a variable in my primary equation. And another secondary equation is this fact that M is equal to, negative B over A, right? Rise over run. We're dropping B units and going to the right A units. Negative slope, obviously. So that might be helpful there as well. So with that secondary equation, with both of those together, I can actually plug, B in for y and 0 in for x, because that's a point on the line. And let's see what that does for me. B minus 5 equals negative B over A, right, for the slope, and then 0 minus 3. And so 0 minus 3, that's negative 3, obviously. When I multiply it by negative b over a, I'm going to get 3b over a, b minus 5. And what I want to do is isolate one of the variables so that I can substitute in for it up here. And so you really have a choice. Like up here, they're equivalent, right? It's just a times b. Neither one is particularly easier than the other. Down here, the way that I did this, if I'd have gone with the x-intercept instead, it'd probably be the other way around. But the way that I did this, it kind of looks like it's going to be easiest to solve for a, right? So I'm going to multiply the a up to the other side, and then I'm also going to divide the b minus 5 down. I'll just kind of do that all at once. So I'm going to get a equals 3b over b minus 5, right? That b minus 5 is like in parentheses, right? It's implied when it's in the fraction. And that means I can now substitute 3b over b minus 5 in to my primary equation for A. And now I have my area of my triangle in terms of exactly one variable, in terms of B. And that means I can use a derivative and optimize. So I'm going to scroll down here a little bit, and we're going to write down our primary equation again, this time in one variable. B times A, 1/2, right? So that B is going to get multiplied on top here. So I'm going to have 3b squared on top. And I'm just going to distribute. I could put the 1/2 up front. I'm just going to distribute in. I don't know. Doesn't really matter. All right. So this is A as a function, A the area, as a function of B the y-intercept. And now what I can do is take the derivative. dA dB equals. And I'm just going to use a quotient rule. It looks like it's set up for that pretty well. Derivative on top is 6b times the bottom, 2b minus 10. Maybe I should have kept that 2 factored out, but whatever. Minus the top, 3b squared, times the derivative of the bottom, which is 2, and then over 2b minus 10 quantity squared. Yeah, I'm just going to have some extra reducing because of those 2's multiplied in. And so I'm going to simplify the numerator. I'm going to expand and reduce. Here I have a 12b squared, and here I have a minus 6b squared. So that's going to be 6b squared. And then when I distribute here, I'm going to have minus 60b. And then on the bottom, that is what it is down there, right? It's factored. I guess I could factor out the 2, which, again, I was saying before, if you factor a 2 out of there and square it, it'll be a 4 on the outside. Maybe I should switch back to blue here. 4 on the outside, and then b minus 5 quantity squared. I keep things factored usually. It's usually better that way. And now I can factor out on top equals 6b and then b minus 10 on top divided by, again, that 4b minus 5 quantity squared. All right, the 6 and the 4 reduce to 3/2 if you want, but I don't really need to do that because all I really want is where DADB is going to give us, critical numbers for the area, which means where this derivative either equals 0 or does not exist. So DADB equals 0 at, b equals 0 and at b equals 10. And it does not exist at b equals 5. And so those are my critical values here. And if I make a little sign chart now for the derivative, we got 0, we've got 10. Whoops, I'm sorry, 5 goes before 10. Sorry, I was thinking of something as I was doing this. And 10. Then we can do a sign chart on A prime or DADB. Now, I do want to point out one thing. 0 doesn't really work here, right? 0 doesn't make any sense because if that's the y-intercept, the area will be infinite. There's no triangle then, right? Cut off any area. And then 5 also doesn't work because, again, that'll give us 2 kind of like open regions that are infinite in area. So it seems like 10 is the option there. Like 10 is the only answer there that's sensible. So you can kind of tell that's it. But 0 is an endpoint of the domain. Actually, not even. 5 is an endpoint of the domain, and it's not even included because we already said our slope has to be negative, so that y-intercept has to be greater than 5. So these are kind of eliminated from contention. And then we can verify that this minimizes the area if we really quickly just do a sign chart here. You don't have to do this if it doesn't ask for justification. But if you want to justify your answer, this isn't a bad idea. This factor is positive. Up until 10, this factor is negative, and this factor, of course, will be positive because it's squared. So we get 1 negative there. I'm going to put a negative. And then once you get past 10, all of the factors are positive. So the whole thing will be positive. So that's positive. So that is, in fact, the minimum at 10. So like the relevant domain for the area function is 5 to infinity, not including 5, because we mentioned that at 5 for the y-intercept here, there is no, it's an infinite area. And then the only critical value in there is 10. And basically our area function we know is decreasing on this entire interval from 5 to 10. And the area function is increasing from there on toward infinity. And that means that this has to be not just a relative minimum, it is the absolute minimum. And so we can say that that's what that triangle is going to be, right? The optimal triangle, and we just got to make sure we answer the question, right? The optimal triangle, the minimum area triangle is going to have b equals 5. And I just mentioned you always, whenever you're solving a problem, you always want to make sure that you actually answer the question that was asked. So it says find an equation of the line through that point that does this. So we now know that b on our line is 5, and then we really just need to figure out, probably what m is, right? And we have m equals negative b over a, and we can get a from here. So you can get a equals b is 5, so it's going to be 15 over, oh, whoops, b isn't 5, b is 10. I was saying 5 is impossible. 10 is our answer for B. And so that means A is going to be 30 over 5, which is 6. Okay, and so A is 6 in our optimal triangle, and that means our slope is negative 10/6 or negative 5/3. And that's the equation of our line. Y equals negative 5/3 x plus 10 if you want to write it in slope-intercept form. You could write it in any form. And I'll just point out one more thing in this video is that a lot of times on these optimization problems, once you see the answer, it's kind of intuitive. Like there's, especially when things are linear or whatever, there's like this proportionality to it. And notice the optimal line ends up having a slope of negative 5/3, and 5 is the y change in y, 3 is the change in x, and the line had to pass through the point 3 comma 5 x comma y. So you can see kind of a little bit of an intuitiveness there. Anyway, that's it.